Okay, it's a great pleasure to have Simone give us a talk on the dual of Feynman integrals. Please start.
Hi, it's a pleasure to be here. I'd like to thank the organizers for continuing this great tradition of fantastic meetings and giving me the opportunity to talk. I will present a work to appear, I think this time it's honestly soon. Work with a student, Andrei Pokraka. It's been work that to do this work, we had to learn a lot. It was been a long learning process of some mathematical tools, and yeah, he did a lot of he did the whole heavy lifting, and with going to share the result of this learning process. So so the general context is we are interested in perturbative scattering amplitudes, where schematically we can write them as some master integrals times some coefficients, and the star of the talk is going to be these coefficients. So the thing which sits in front of these masters. Specifically, we want to understand how these coefficients can be extracted from cuts. So we'll be interested in methods for extracting these coefficients. So that's in the spirit of generalized unitarity that I will present. And the overall message of the talk is that these coefficients live on a space of their own. So there's a space of Feynman integrals, and then there's this dual space. And actually, you can do a lot of operations on that dual space, and you can learn about it by the space is somewhat simpler. So, yes.
Simone, we're having a little problem. Maybe a suggestion is turn off your video, and then maybe we can hear you better.
Yes, I've tried that. Is it better now?
I think so. Anyway,
okay, so,
please continue.
Yeah, so what's the outline of the talk? So I will review a bit. I don't think we have many talks on this this year, so I will review a bit the general ideas and the general goals of what we do. Then, I will try to explain really the core of the talk would be on basically how to explain to a mathematician what's a Feynman integral. And I think we have a viewpoint that's going to be very useful in the future. And then I would show some results, which, notwithstanding my first slide, are mostly about one loop at this moment. So the success story that we're trying to generalize is the story of generalized unitarity for one loop integral near dimension 4, where it can be written in the form of a rational term plus bubble, triangle, box, sometimes tadpoles. And the main point is that the coefficients can be expressed as product of unshelled trees. So this is something that I find extremely appealing as it's a thing that's been attracting me to this amplitude field from the beginning, is that it allows you to build observables from simple observables. These unshelled trees are not like vertices in Feynman graphs. They're really the observables themselves. And yeah, this story has been generalized. You can extract it built on previous work on generalized unitarity by Zvi, for example, and the collaborators in the 90s. And yeah, there are formulas for bubbles and rational terms and so on. And that's a story we'd like to generalize to two loops. It's not so straightforward. One of the first thing, which is obviously hits you in the face, is that there's no obvious unique choice for natural basis. There's nothing like the basis of scalar integrals at one loop, which smacks of uniqueness. So whatever you do, you have to do some arbitrary looking choices. But you make these choices, and then sometimes you can find residue formulas which extract coefficients. Then you find that these residues are not unique. There are many ways of extracting the same information. And usually this can be done for like the topology with the most propagators, where you cut everything. But having residue formulas for subtopologies gets trickier and trickier. You have to disentangle contaminations. And 2 years ago, there was a beautiful paper by Paulo and Sebastian, who proposed that basically a different way of looking at things is that we should look at if someone gives you a formula for extracting some integral coefficient, you should look at this formula as a representative of some cohomology class. And then all these ambiguity are the usual ambiguities in finding representatives. And yeah, we should think of these C's as living in a space of their own. And instead of starting by postulating what is the integral whose coefficient you want to extract, you just make a list of all the information you can extract. And then you figure out how to pair that information with whatever integrals are in the basis. So it's a very different way of looking at things. And yeah, and our motivation for looking at this that way is that really we want to keep going with this program at 2 loops to build observables from simpler observables, simpler ones. And we insist we want to do that as on-shell as possible. We would like to understand from an on-shell perspective, what can we say about the analytic structure of transcendental equations, of the transcendental functions which appear. We'd like to get basically as much as possible information from the cuts. And eventually we'd like to understand, it's great to have formulas in terms of d-dimensional observables. Eventually we'd like to be able to handle epsilon of epsilons and phrase things directly in terms of things we actually observe in 4D, but that's a long-term dream. So for this talk today, we're not going to be in dreamland, unfortunately. We'll be working in 4-2 epsilon dimension. And when I refer to an integral in this talk, I'll be looking at integrals integration by part identities. So I will mod out by all integral identities, which means at one loop that the formula I wrote is not actually the one I will generalize. So if you mod by ABPs, there's really no such thing as rational terms. Instead, it appears as the order epsilon coefficients in the other things. So today the target is to be a formula like this bottom one, where everything makes sense with epsilon dimensions, but all the coefficients are some rational function of epsilon. And the goal is to try to understand these coefficients. So the intersection approach, the whole idea of it is that to make some kind of pairing between the space of loop integron modulo IBP, which is the thing that matters for the answer. And the basic idea is that this pairing is such that it's automatically compatible with integration by part identity. So anything you write that is of this form is going to kill IBP identities. So that takes care of the biggest constraint on these forms phi. And the other thing that's nice about this intersection pairing that we'll explain more briefly is that it's completely algebraic. Like one might have thought that the dual of the space of integral is the space of integration contours. And with our talks where people think about the space of possible integration contours and monodromy and all that, and that's all great, but and it is true that the space of homology or space of contours duals the space of integrals, but this is another space. The space of dual forms is another space that is also dual to integrals, and they are not homology classes. They're not cycles. And the reason that's going to be useful for calculations is that we can do everything algebraically. Whereas if you start playing with integration cycles, you have to do integrals, and that's a transcendental operation. Everything we do will be algebraic. So that's the great thing about this approach. So you can extract coefficients using algebraic steps. So much of though here is maybe a bit more for the expert, but to review a bit the context, much of the work so far with this intersection approach, I've used the following theorem, which follows from a theorem proved by a mathematician, Matsumoto, which is that if all propagators have non-integer exponents, so in 4-2 epsilon dimension, epsilon is not 0, but also all the propagators have some little delta that you add to it. If you're in the setup, you can show that the space of dual integral is exactly the same as the space of integrals. And you just have to flip the epsilon somehow. And so basically the space are the same. So this intersection is literally a pairing between integrals and integrals. And so once you have a basis of integrals, you can invert that pairing and use that to extract the coefficient. That's been used successfully in many two-loop examples. Today, we try to go beyond that trick. And the reason is that ultimately, if there's one thing we learned from this amplitude business is that the sum of all Feynman diagrams is nicer than the individual ones. And this trick, the problem with it is that it doesn't go very well with the idea of summing all Feynman diagrams. We like to have a method that allows us to combine all the graphs together. And basically for that, we have to go back to the undeformed problem. As far as at least I don't see how to do it otherwise. In case it's nice to be able to study the problem. The problem is already deformed a lot in my taste by adding epsilon, so I'd rather not add an extra delta. So our goal would be to do that. And the claim is, that's a mouthful. The claim is that this dual forms, they live in the compact support cohomology of the complex plane minus the place where twist vanish. And so yeah, twisted cohomology relative to propagators. So basically the goal, the body of this talk would be to explain all the words in that sentence. Okay. And then I will flash some results at the end. So I want to explain the following. So what's a, I'm going to use methods of algebraic geometry. So what's a differential form in 3.99 dimensions? Why are we going to use cohomology? Why is it twisted cohomology? Why are the dual of Feynman integrals? Why do they have compact support? How are they computable? How does it relate to, why is the space the same as that of relative cohomology? And why is that useful? I want to explain all of this. And I want to emphasize that I think that the nice thing is that we only need the mathematic textbook definitions that would be understandable from a mathematician or from a 1950s algebraic geometer. So it's not like the everyday math from physicists, but we're not also going to need we don't need to invent anything. That's an important point. So yeah. So first, let's explain what's an integral in 2.99 dimension. Well, really, we just need two properties of dimensional regularization, which, as defined by Theof and Feldman, one of them is that we can break apart the loop integral into usual integer part and extra bit. So really, you just have to define the extra bit, and you're done. And what's an integral in a fractional number of dimension? Well, if the integral depends only on the norm of a vector, then it's very easy to do. You just switch to angular and radial variables, and you just have to keep the radial variable, and that's what we mean, right? So when that's literally what we mean by that's what we use when we calculate Feynman integrals. And yeah, Theof and Feldman proved that the definition is compatible with this way of splitting integrals. So in terms of differential forms, that means that an integral in 4 minus 2 epsilon dimension is really a 5 form. So we have our usual 4 integral times this extra dl perp square. So that makes it the 5 form. And it has 3 key properties. The first is that it's algebraic, because our propagators are algebraic in flat space, at least in flat space. The fact that it's algebraic means that we're going to complexify everything, and that's why we use cohomology with complex momenta. The integral has poles, right? Propagators blow up, especially when you allow the momenta to be complex. They blow up at various places. So it's really a form that's defined in the complement of these are propagators. It's a form defined in the complement of where things blow up, where propagators blow up. Okay. And the next thing is that there's this thing raised to a fractional power. We call this thing the twist, or u. So in the complex L-perp square plane, this is not single-valued. So our integrand is really a multi-valued function. And that makes it twisted cohomology. So the way you could denote this is that way. So this mathematical definition is just summarizing these three key properties of Feynman integrals. I want to emphasize one thing. In this talk, I will eschew the use of parametric representations. And the reason I do that is not just because I want to be fancy, is that ultimately I'm interested in combining all the topologies together. And I find that parametric representations are a bit, don't play very well with the idea of combining diagrams. So they usually work diagram by diagram. So that's why I insist to do everything in the original momentum space. And yeah, I think that's there's something I observe very often when physicists interact with mathematicians, and mathematicians ask, what is a Feynman integral in d dimensions? Often the go-to answer is to go to introduce semantic polynomial, go to parametric representation, and declare that clearly this is all well defined. And I think it's okay to just give the straight answer. It's a d-dimensional integral is defined by this, and it's clearly well defined. That's what we mean. And of course, definition generalized to higher loop. One has some Gram determinants. It's closely related to the Backcroft representation. There's a nice derivation in this paper. You can read about that. Yeah. So why are we going to care about cohomology? Is because we only care, well, I declare that if we only care about integrals modulo integration by part identities, well, they saying that in dimensional regularization, total derivative integrate to 0, that's saying that integral of something exact is negligible. So what we care about is space of integrals modulo exact differential forms. These are total derivatives. And basically everything we do are closed form, top form, so that makes them closed. So we care about cohomology. So cohomology is a fancy word for saying work modulo integration by part. That was easy to answer. Why is it twisted cohomology? It's because of this regularization, which makes our form multi-valued. In practice, a good way to deal with that, instead of worrying about the branch of L-perp to the 2 epsilon, so this is what we call the twist U. So we just pull this out and we say that the form is this times something that's single valued, and then we deal with the single valued form. But then when you integrate by part on the single valuedness, your total derivative picks a d log of u when you commute it across. So if you focus on the single valued form, then what we're interested in is forms that are closed under covariant derivative modulo those that are exact. So that's just twisted mean. It's just the usual covariant derivative thing. And the form is exact, so we still have nabla square equals 0. Why does the dual have to do with compact support? This is almost tautological. So our goal is, I've defined to you so far the space of Feynman integrals. And well, obviously, if I give you another n form, you can get a number by integrating over all n-dimensional complex space. So there's an obvious way to pair forms. That's the intersection pairing. It's just the dumbest way you can get a number. And basically, right, it's tautologically what the duality is, what the dual space is the space of dual forms is the space of forms for which the integral makes sense for any integral I. So if I give you a phi such that the integral makes sense for any I, then that's an element of the dual space. And the issue is that these I's have poles. Since the Feynman integrals have poles in their propagators, then these dual forms need to vanish there for the integral to make sense. And that's it. So that's why by requiring the forms to be compact support, we're basically requiring them to vanish in some neighborhood of the poles, and then makes it possible to integrate by part. And then this integral makes sense. But then it gets tricky, because how do we compute anything? If we're going to look at forms that are, like, the things we like to work with are holomorphic forms or things that are algebraic. And now I'm telling you, you have to look at forms that are compact support. So they have to be function of loop momentum and a complex conjugate of loop momentum. That looks bad. And here's where the algebraic geometers come to the rescue. They've been struggling with this problem for centuries, and they've solved it. And okay, I'll tell you our interpretation of the answer is that basically you introduce the following distribution. So if I give you any holomorphic form, you can make it compact support by slapping a step function into it. So theta is going to be a step function that vanishes that has support outside the little disk. So it's just removing the singularities. So if you slap any form with that, it's compact support. But then it may not be closed, because when you check that it's closed, you get this derivative d theta, which is this d theta is like a circle. So we have those two things. And the claim is that you can concentrate all of the dependence on z bar variables into those two things. So there's a z bar hidden into that because it's the absolute value of z. So there's a dz bar hidden in there. And the claim is that all you need, this compact support cohomology is spanned by these two guys multiplied by algebraic things. So you don't ever really need to write down a z bar. So that's what we're going to use to do calculation. Here there's the last thing we need to define, we're going to do calculations with, is that suppose that D is some propagator, then all the dual forms need to have a 0 of that propagator, so they're proportional to that step function. But when you start integrating by part, I told you that grad of something is negligible, but when you commute grad across a step function, you get this delta function thing, d theta. And one way to think about this is that this really equivalent thing that there's a little boundary around each of these places. So really, what we're doing is the same as saying that each possible propagator is going to act like a boundary. And if anything that multiplies a d theta is something that lives on the boundary. So there's a word for that when mathematicians call a relative cohomology is like differential forms where you pay attention to boundary terms. So you can do that, and that's at space. So that gives us a clear way of thinking about these dual forms. So at one loop, it's going to be a combination of these things. It can be either a 5 form in the bulk, or it can be a 4 form that lives in a single cut. Or it can be a 3 form on a bubble cut, or eventually a 0 form on a pentagon cut. And the space of dual forms is a direct sum of all that. They talk to each other a bit, but not so much. And all the forms are, and all these forms are pole free. So we're basically writing polynomials supported on these cuts. That's our space. So before we tell you what to do with physics, what this has to do with physics, let's let me somehow summarize the 3 operations we need. So all of these were defined by Leray in the 50s. One is the one I just described. If I give you so if you have some boundary, like on a cut, you can make a higher dimensional form on the bulk by wedging it with the delta function on this little circle. So that's a so-called co-boundary map. I'm going to use that a lot. And the reason it's useful is that it's basically a dual to taking residues. So if you have a form that lives, if phi is a form that lives on a cut, you take its co-boundary and you intersect it with some integral, it's just going to take the residue of that integral. And that's because d theta is like a circle. So the integral is going to be a little circle around the pole. So yeah, and the last thing is that when we do integration by part with the boundaries, we have to keep track of boundary terms. So we get this delta function terms. So all I want to say is that the operations are canonical, which is great because it means that whenever you can like think about commuting operations, they commute. There's a lot. You can think of all these letters, theta and delta, as they're related to. There's a lot of isomorphisms that we can build on from the math literature. Yeah. So Jean Leray did a lot actually of the foundation of this work during while he was a prisoner in Austria. So while Lars Ansager kept busy by solving the Ising model, then Lurie was computing some loop integrals. Mike C. So we'll see. Oh, I have a lot of time. It's been faster than expected. So here's a sketch of results we obtain. So okay, the first result is let's forget everything we knew about one loop, generalized unitarity, and let's just classify these dual forms at one loop. Let's see what space there is. And in fact, we can completely solve the problem in 2 minutes. It's completely it's really easy because of what I told you 2 slides ago. If I go back, I told you that dual form is a combination of things with basically polynomials which live on cuts. And in fact, it's real to see that if you don't have any cut and just writing down a polynomial, then you get 0, right? Everything is a total derivative. So an integral without the propagator is trivial. So because this term vanished, everything you're gonna have live on cuts. So in one line, you've basically proved that the basic thing about why on shell appears is that if you leave everything off shell, this cohomology is 0. There's no, all of these dual forms are going to live on cuts, just because of that result. Now you start looking at cuts at one loop, and you know very well that when you take a unitarity cut from the Kotkowski rule at one loop, so if you have 2 propagator, what you get is a sphere. So in general, at one loop, all the IR cuts are spheres. And there's a nice lemma that the cohomology of sphere is just one-dimensional. And it's actually 0 when if the sphere degenerates. But generically, it's one-dimensional. Here, it's a slightly unusual complexified sphere, but it's actually the same result. So basically, we just have to list the possible spheres in the problem, and that gives us a basis. So that's it. So the basis of, we just enumerate the cuts. That's a basis of dual forms at one loop. So I'm going to give you an explicit basis. So in general, you have you have the dual of a tadpole, dual of a bubble, dual of a triangle, and so on. The dual of a bubble explicitly, what is it? So it lives on the solution to propagator d1 equals 0, d2 equals 0. So I put those 2 delta functions. And then normally the bubble cut will be a 2-dimensional sphere. But because we're on dimensional regularization, we also have this perp direction. Effectively, we have a 3 form. So, and this is just like the equation of a sphere downstairs. So that's yeah, and the power was chosen so that this thing kills nicely triangles and box. We'll see in a second, but basically that's our form for the dual for the bubble. That's our form for the triangle. It lives on a triple cut. And there's 2 variables left, so it's a 2 form. The dual for pentagon now is a 0 form that lives on a 5 cut. And obviously, you cannot write down any dual for an hexagon because you just have 5 variables. You can't cut 6 things. And that's it. That's the basis.
Simone, how much time do you need?
Oh, shit. Yeah, I'm supposed to be, it's over now, right?
Well, you should definitely explain the punchline. Whatever
okay,
you do.
Yeah. We'll skip. Yeah, sorry. I screwed up for the timing. Okay, yeah. Okay, yeah,
I mean, we'll give you a little more time, but
okay, I will skip in. I think in 2 minutes I will finish. So one of the punchline is that yeah. So one of the punchline is we can get differential equation from cuts, and usually when you get yeah, I'll give a punchline here and then be another 1 second. But yeah, usually when you
take your time. You know, don't overrush, but
okay.
be quick.
Yeah. So it's well known that integration by parts simplifies a lot when you're on maximal cut. Normally, it's a result of moderate use. Say, for example, you cut all the properties in this box. Integration by part identities become trivial. But then if you try to recover differential equation from that, well, you've on this cut, you've killed a triangle and bubble, so you don't get any interesting information. So you lose all the off-diagonal terms in this differential equation matrix. It would be great if we could somehow do IBPs only on the cuts and yet recover all of these things. So it would be like heating our cake and having it too. And you can, and what you need is a dual cake. So that's the magic with these forms. And the reason I'm going to flash this slide is that the differential equation for these dual forms is the transpose. So I'm going back and forth in 2 slides so you can see the zeros are moving around. So these dual forms satisfy the transpose equation. So if you sit on the triangle cut and integrate by part, integration by part is going to be trivial, but then you're going to recover the box term here, mixing to triangle and box from some boundary term. So you're just looking at polynomials on this triangle cut and you get the box. So we realized this had to work and we tried to do it, and it at first it seemed crazy, but when you really try to do it, it actually works. It's really amazing. So yeah, I'm just writing an integration by part identity just to tell you that they basically are fixed by spherical symmetry, right? We have this form. If you vary the parameter, the only thing it can happen is you change the radius. And if you change the radius of a sphere, it's easy to like write an IBP vector that cancels that. That's this guy. But then when you have this IBP vector, you have to go back to the work of Lurie and you discover that you get the boundary term. And then this boundary term is the thing that tells you with the mixing with the box. And you can just read off the coefficient. It has a nice D-log form. So using this method, we constructed the general differential equation satisfied by one-loop integral in any dimensions. The function, it comes out naturally in canonical form. And a lot of these entries are simple, are simple to understand. Like in 1850, Schlafly computed the derivative of the box integral and found it was derivative of an angle times a bubble integral. That's this term, we reduce it. A triangle, of course, is a box with a point at infinity, so it's the same formula. And 0 is like point at infinity. A pentagon is like an hexagon with a point at infinity, and also discussed that. So most of these terms like this. The diagonal are fixed by dimensional analysis. And this term is the one we computed on the previous slide. And basically, yes, this is the general answer. Apparently, it's new, but it's not, as you see, there's not a lot of completely new juice. And yeah, so we can write down the differential equation satisfied by arbitrary one-loop problem. And the other thing that we have discussed is can get formulas, residue type formulas that extract bubble coefficients or triangle coefficient, the sort of things in d dimensions. I just want to give you a flavor. It's like the trivial problem you can ask is like, suppose you have a function on the 2 sphere, you're trying to do symmetrical integration, you're trying to average it on the sphere. We have to do that all the time when we look at when we extract bubble coefficients. And basically the problem is, yeah, try to find the average of this polynomial. And I'm going to skip detail of the solution, but the sort of solution that comes out of this is that you write x and y as you make complex variable x plus iy. And then you have a residue where this complex variables go to infinity. And then the other goes to 0. And you can extract the, you can do symmetrical integration by doing these residues. So that's, yeah, and you can check this formula. It's a very elementary formula. The function you need is some arc tangent, but you're expanding it around a point where it's just a regular series, 1 over t. So you can reproduce the classic result that the average of x squared is 1/3, for example, and a lot of other nice numbers. So it's very similar conceptually to the BCFW poles infinity. We're going to complex direction to infinity. There's a lot of formulas that are possible. Basically, by choosing different representative of this cohomology class, you get different formulas. You get the triangle cut contribution. Disentangling the bubble from the triangle, there's always an extra term in these formulas. You get it automatically when you account these boundaries. And the thing which is kind of intriguing is that this bubble, like we know that the bubble has a lower transitional weight compared to the box integral. So there's a reduction. The form has a reduced weight. And what we're saying is that the dual has increased weight in exactly such a way that the product, the intersection between the bubble dual and the bubble form is supposed to give you a number, a pure number with weight 0. And really the way it works is that one of them has higher weight and the other has lower the weight.
Simone, you need to leave some time for people to, good, okay. People need to ask you questions.
Good. Yeah. So the main message is that integral quotients live in the space of their own. This space knows about differential equations, knows about coefficients from generalized unitarity, and it's really best to study that space on its own right without really referring to an integral basis. It's just we're looking for a basis of this dual space, and yeah, there's some directions for future work. Yeah. Thanks.
Okay, thanks a lot, Simone. Let's thank him. And we should try to get a couple quick questions in, but I think there'll be more, people want to ask more. We can do that during the break.
Yeah, so we can do that.
So let's see who's raising their hand. Actually, I don't quite see, but I know, see, Julio had a question.
Hi, Simone. Thanks for a very interesting talk. I just wanted to ask about, so this twisting in the Bykov or the parametric story plays a very important role because there's a lot of kinematic dependence in it, and etc. But here it seems that you just have this L-perp direction. So do you want to comment on that?
Yeah, correct. Yeah, the only twisting here is the L-perp direction. So,
right.
so yeah.
What does that imply, for instance, for the fact that the forms are twisted instead of untwisted?
Yeah, I think, yeah, it's still regularizing things at infinity. Like this, yeah, I mean, I guess you're asking what happens when we take epsilon goes to 0. And presumably, like in the same way that when we take this propagator powers go to integer, we discovered that we needed to add some delta function around the where this distribution that are like delta function around propagators. Now, presumably, when you take epsilon to 0, you need to add like delta function at infinite momentum or things like that. So we don't have I don't have a clear picture, but there must be also some way of understanding the limit.
I see that there's many questions from many people. I will probably just pick one person randomly, and then we can do it during the just continue the questioning. Yeah, during the break there'll be some time there. So okay, I just to pick someone random. I see Matt von Hippel. Why don't you ask your question, and then we'll have to go on.
I was a little curious about sort of prospects for going to higher loops. So your last slide seems to make it sound like your expectation is you just need to figure out each loop once, individually. Do you think there's any hope for some more general overall approach?
Well, probably you know that better than me, but yeah, my personal experience, yeah, the reason I wrote this words is that I try a lot to understand the geometry of two loop integrals, and it's like you have one sphere, but they interact with each other in a crazy way, and I just can't wrap my head around the geometry of two loop integrals. But if I do one loop at a time, then I think I can like say things. but maybe there's a way of doing it more directly. Yeah.
Okay, thank you.
Yeah, actually, I see the break is 45 minutes, so maybe I'll just pick one more question, And then, so I see David Kossauer. Would you like to ask a question?
Actually, I noticed that Rob Schabinger and Giulio Salvatore had their hands up before me, so I'll wait until the break.
Okay. Oh, okay. Then, sorry. Oh, where was it? Yeah, Rob, how about you?
Thank you very much. Thank you, David. Thank you, Svi. Can you guys hear me?
Yes.
Yeah, go ahead,
Good.
please.
So 2 questions, really. As you know, I'm particularly interested in the applications of your work to differential equations. Have you thought at all about any possible connection to the so-called Bykov approach? Because I noted in your paper that you're also expanding about epsilon goes to infinity. And, so that's part 1. And part 2 is maybe sort of a bit along the lines of what Matt was getting at, but with differential equations. What do you see the prospects being for higher loops with the differential equation approach? I mean, and maybe I can make it more concrete, actually. Would you be able to realize, for example, Roman Lee's construction, where he would say that in any dimension, you can either get epsilon form or epsilon plus 1/2 form?
Yeah, I'm not so sure. So the first question is a simple answer. So you can. I chose arbitrarily to write the integral as a d4L times d minus 2 epsilon. But of course, if you're interested in problem, we have fewer external momenta which don't span the full 4 dimensions. Then you're free to write this as dl times d3 minus 2 epsilon and just have 1 dl per loop. Yeah. And that's basically the Bykov representation. So yeah, this is totally compatible and then basically equivalent to Bykov if you want.
Now, just to be clear, Simone, I'm not referring to the Bykov representation. I'm referring to his integral reduction method that he used for the 5-loop beta function calculation.
Yeah. Okay. Yes.
So there, he actually did an expansion about epsilon goes to infinity.
Yes.
And I saw in your paper that this was a very important ingredient. So I was just wondering if there was any connection there.
Yeah. That's actually in the paper by by Andre and Misera. I was not on that paper, but indeed. So Andre tried a lot to do this expansion around large D. It may be that it depends on the class of integrals you're looking for. For integrals with many external legs, the difficulty was the critical points were really hard to find.
So you're referring to the fact that the Morse functions had not isolated critical points, or what?
No, I think even when they are isolated, they're pretty hard. I mean, you can't really solve them symbolically in terms of S and T. So so if you put you can solve them numerically, but then it kind of defeats the purpose of the approach to if you have to solve numerically for critical points.
Mm-hmm.
That was a difficulty. Yeah,
Okay,
but
good. Thank you.
Yeah.